X7 Phenomenological forces. In nature, there are four fundamental forces. Newton found that gravitation, universal gravitation, and they have found electricity, the electrostatic force, and magnetic force. And because of the special theory of relativity by Einstein, these two theories, electricity and magnetism, they are combined into a single unified theory that is called electromagnetic interaction. And then we have nuclear force. That means inside the nucleus of an atom, we have neutrons and protons, and they are consist of quarks. And they are the fundamental particles rather than the proton or neutron. They can be broken into pieces consisting of quarks, and they are connected. They have interaction through the communication via gluon. So that gluon is just like a photon in the case of the electromagnetic interaction, that is a messenger of the electromagnetic force. So anyway, nuclear force consists of a strong, that is related to the quark interaction through gluons, and weak interaction. They are governed by the heavy particles messenger called the W or Z0. And these are absolutely different from the other interactions. It is a very short range interaction. So it is a nuclear force. So all of these are called fundamental interaction, elementary interactions. But in our usual life, everyday life, we encounter phenomenological forces that are not fundamental, but very important for us. Without friction, we cannot stop, and there will be many, many car accidents, for example. So it is a very, very dangerous. Just like that, today we focused on the phenomenological forces rather than elementary forces. Simple example of phenomenological forces is tension. Tension is the interaction between two objects that communicates with some force. If you play a tug of war, you pull the rope and the other person pull the rope in the opposite direction. So you apply your own force in this direction. Why don't you say it is you are named as one and the other opponent is two. You apply some force and you are applying some force to somebody else. And this is a vector. And on the other hand, this guy applies some force to you. This is a kind of action and reaction. When the rope is broken, this communication is broken. As long as the tension exists, you share the same amount of force, but in opposite direction. Therefore, the tension, we only write it as a magnitude instead of direction, because tension is correlated to forces that are connected as an action and reaction. So action-reaction pair, their magnitudes are the same, however, the directions are opposite. Okay? So why don't you consider this object in here, unstretchable string. So length of a string is invariant. Mass of the pulley is negligible. This pulley, you just forget about the motion of this pulley and ignore friction. So we don't lose any energy. The gravitational acceleration is g and is heading toward the parallel to E2 hat, and the unit horizontal vector is E1. Okay, all set. First of all, let us consider the equation of motion of the first particle. This one, even though there is a gravitational force, because of the normal force that sustains the mass, we forget about the vertical component of force. The net force does not have any vertical component. So effectively, F net force, algebraic sum of all of the forces applied to this object is sum of these three, and this is a tangent, and whose direction is along the E1 hat. So sum of these three forces are net force applied to capital M. Fortunately, we have exact cancellation, and F net on this object is exactly the same as TE1 hat as it is written in here. Because F net is this, F net is always expressed as ma, mass times acceleration. And it is moving to the right, so the coordinate x appears as double derivative, and we have a unit vector along the horizontal direction. So this is a complete equation of motion for capital M. Why don't we consider the equation of motion for small m? Small m has its own mass, and gravitational force is applied along this direction. And then we have a tangent, this tangent, the magnitude of the tensions are the same as long as the pulley is negligible. The mass of the pulley is negligible, and because we ignore friction, this motion of the pulley does not contribute to the whole system. So it is completely decoupled. So you forget about the interaction. Instead, it gives some normal force. This normal force allow the change of the direction of the string. By the way, if I ignore this part and concentrate on this small mass m, what we need to consider is net force. That net force is the sum of tangent that is along the minus E2 hat. T is always a positive definite. It is going upward, and gravitational force is mg. Now g is written here. I replace this one with mg multiplied by E2 hat. Because T tension is opposite to the gravitational force, I put the negative sign in here. Okay, we can find these are the unit basis vectors, and if two vectors are the same and they are expressed in terms of basis vectors, and then the components are uniquely defined. Therefore, I can read it to find mx double dot equals mg minus t. In here, capital M x double dot equals capital T. Okay, by the way, the distance from here to there is a y, but because the string is unstretchable, x and y are the same. So I have eliminated y and substituted x for y to have only a single variable x. By the way, what we really want to know is both x double dot and tangent. So we have two unknowns and the two linearly independent linear equations. So from middle school, we usually used Gaussian elimination. If I add these two, then tangent cancels. So in such a manner, I can solve this equation. Or you can find out that you can solve the equation for both the x double dot and t. This is because it is a system of linear equation by making use of matrix. You can eliminate t by adding these two equations. You arrive at left-hand side. It's a capital M plus small m multiplied by the acceleration x, and right-hand side mg. Therefore, we arrive at x double dot, the acceleration is uniform. Once you know this, and we can substitute this one in here to find the tension. By the way, the tension is expressed in such a manner. Tension is m times m double dot, small mg, m. Aha, what's that? It is weighted by the gravitational acceleration, and the coefficient is product divided by the sum of the two masses. We have a special notation mu that represents the reduced mass. This is the general formula for any two-body interaction. And for example, our sun and Earth is rotating around the sun, and Earth is a very, very light in comparison. The sun is very heavy. What happens if m and small m goes to infinity in comparison with the small m? This reduced mass is dominated by mm, m in the denominator. This one disappears, and this mm cancels. The mass of the reduced mass is reduced to the Earth mass. However, if the two masses are exactly the same, what happens? This m squared divided by 2m. The answer is 1/2 of m. So in general, if the two masses are comparable, this reduced mass is less than the bigger mass. Okay. However, if the mismatch between the two masses of the two-body system is extreme, then the reduced mass reduces to a light mass. And this relation we have, perhaps if you in middle school, you must learn about the harmonic average. The origin of harmonic average is this kind of two-body interaction. So what we just have eliminated one unknown and determined one another unknown, and then substitute the final result to determine the undetermined unknown. It is called Gaussian elimination. Anyway, consider the system m plus m, including the string, whose mass is negligible. Then the net forces, okay, let's see. What are the net forces? Including the string, what we have in here, we have mass, this one mass, so gravity, this gravity cancels, so don't forget about the gravitational force applied to here. And what's that? This one, this tension does not apply any force to itself. It can apply some force to this mass or pulley. Then actually, if we introduce this pulley behaves as it contributes to the system applying this normal force that is normal to the pulley's surface. Okay, so because this pulley sustains, this string can bend. Okay, so the net external force on the whole system is, where is it? Normal force, and mg. You know, capital mg. This one does not contribute because what's that? Because the normal force on the floor cancels the gravitational force applied to capital M. Therefore, if I consider these two masses and including the string, the pulley applies some force that is normal to these circular, the rounded part. The normal force is applied along this direction. So net force on this two-body system, including this string, is actually the normal force plus mg. By the way, we know the actual motion of these two particles, these two objects, that is capital M multiplied by x double dot along the horizontal direction, and this guy accelerates downward, that is along the E2 direction. So because I know everything in here, by making use of this information and this information, I can determine what this normal force applied by the pulley to the system. This is simply a subtraction. Subtract, add minus mg to both sides, then I can find the answer. That is this. Okay. Finally, we go back to the answer for the tension. In the limit, as m is much greater than capital M, what happens? This one is very heavy and this one is very light, and the tension is not strong enough to sustain this. It is this guy, because it is a very heavy, the mass capital M does not apply enough force through the tension. Because of that, this one is just like falling freely. Therefore, the motion tension, what's that? Here, small m is very large, so I can remove this. And then small m cancels. And finally, what I get is capital Mg. Let us substitute in here x double dot equals g. What's that? That means it is the acceleration of this block is just like freely falling body falling along this direction. Okay. Next, capital M is much heavier than small m. If it is very heavy, it cannot move. It is just attached. It is just like a wall, infinite mass attached. So the tension should sustain this one. Do not let this small m fall down. That means that there is an equilibrium between the tension and the gravitational force. So tension in this case, must be small mg. And applying the limiting behavior, we reproduced the physical solution in that limit. Next, we consider the motion of a bead, and it is constrained to move on a circle, and this circle is on a vertical plane, and gravitational acceleration is downward. Describe the motion of the particle. It is convenient to define the following unit vectors if we know this one very well. And they are unit vectors, unit radial vector and unit tangential vector that can be translated in here, and they are always perpendicular to each other. The magnitude is 1, and we have a radius r, don't forget. Therefore, the position vector of this particle, point P, can always be parameterized by r is a constant radius, and then er hat unit vector along the radial direction. We can compute the derivatives for er and e theta, and we know this one very well. Therefore, this velocity, because r is constant, r dot equals always 0. Sure, r double dot is also 0. Very simple case. Therefore, the velocity of this particle is a radius multiplied by angular velocity multiplied by the unit tangential vector. Okay. If I do the same job, but we apply the derivative one more time, I can find the acceleration. The acceleration is, as we have already computed so many times, opposite radial direction toward the center, negative sign, and it is r omega squared. Here, omega equals the theta dot. Theta dot does not have to be a constant because it is on a vertical plane. Fast, slow, fast, slow. It is not a uniform circular motion. It is not a non-uniform circular motion on a vertical plane. Therefore, if it is a uniform circular motion, this term does not contribute. However, in our case, angular acceleration exists. If it goes up, slows down, and goes fast, slow down, fast, slow. In this case, because of that, we have an angular acceleration exist, especially in here, angular acceleration, if I rotate and counterclockwise, it slows down very quickly and it accelerates very quickly. So this is the maximum angular acceleration appears. And in here, angular acceleration does not appear. So at these 2 points, it can be approximated as uniform circular motion, or top or bottom. So centripetal acceleration minus r theta dot er squared. This one is centripetal acceleration, and we also have tangential acceleration that changes the angular velocity. By the way, because I have computed acceleration, if I multiply mass to the acceleration, it is always identical to the net force on this system. Because this object has a mass, it feels the gravitational force, and it is constrained to move on a circle, and there is no friction at all. No friction. Without friction. Therefore, the track exerts any kind of force only along the perpendicular direction relative to the motion. So, therefore, the constraint force is always normal to the track for the circular orbit that is just radial direction. And this tangential direction does not have any contribution from normal force. So in general, at here, normal force is along this direction or this. I don't know whether it is to the left or right, but normal direction is here. if it is in here, normal direction is this, and the gravitational force is this, and on top of this, normal force up or down, and gravitational force. Aha! So in here, net force is always on a vertical direction. So that's the reason why only at these 2 points, this motion can be approximated as a uniform circular motion for a very short time. Anyway, we just substitute what we have found. This is acceleration multiplied mass is the net force, and this is just a copy of the previous result by finding the acceleration. Next one is finding the net force from the system. We have gravitational force and normal force. Okay, so this sum must be the MA. MA is copied in here. This is radial direction, unit radial vector, and this is a unit tangential vector. Now let us apply the completeness relation. Normal force has only a normal direction relative to the track. So this one-dimensional completeness relation says normal force must be proportional to ER. That's it. And ER is given in here. And we apply completeness relation into dimension for the gravitational force, gravitational acceleration, and gravitational acceleration G is downward, and whose direction is this. So G vector is minus G multiplied by unit vector along the y-axis. So anyway, this G can be expanded as a linear combination of a radial and tangential. And there is no coefficient at all. What we need to do is just compute the scalar product. It is trivial because a G is a this. So what we know, this is ER and this is E theta, just multiply by this scalar product. The coefficient is sine and cosine, okay, over a negative sign appears. As a result, normal force is net force subtracted by mg because of this. We find normal force as F net force subtracted by m. Using this method, we can determine the normal force in this manner. You can find, depending on angle, this normal force varies. Okay? By the way, because the normal force is always along the radial direction, let's see. Normal force is expanded in radial direction and angular direction. Haha! Because normal force is always along the radial direction, this guy must vanish. That means it is exactly zero always. And we find this equation. And actually, we define angle theta from the horizontal direction, but if we measure the angle from the vertical direction, this cosine becomes a sine. Okay, in that case, this equation is identical to the equation of motion for a pendulum. That is, theta double dot plus a g over L sine theta. And when angle theta is very small, sine theta can be expanded as a theta minus 3 factorial, theta cube, and so on, small angle. So it is approximately theta, and it is identical to the simple harmonic oscillator. Okay? And then, if you, so this is gone. and we determine the normal force. From here, we can determine the force. Okay, so depending on angle, when angle theta equals zero, so in here, what's that? Theta equals zero, we find minus mr theta dot square. What's that? Aha, in here, it is just like rotating about this direction. So the normal force is the only force that let these track curved on a circular track. So normal force is a horizontal direction and toward the center. That is the centripetal force is coming from the normal force. What happens if I have a theta equals a 1/2 pi, then it becomes a maximum g, or minus 1/2 of pi, it is a minus something like that. Anyway, in here and there, you will find the normal force varies, and you will find normal force at here is greater than the normal force at here. Because the gravitational force is always the same, but this is rotating very fast on the bottom, and then the circular motion is generated by the centripetal force toward the origin. Therefore, to win the game, this normal force and gravitational force, this sum must be the net force to make this uniform circular motion. So this normal magnitude of normal force is very large on the bottom. So if you construct this kind of structure, here, this part must be stronger than there because the normal force, we do not require very large normal force in comparison with the bottom.